over to you. Take it over.
Hey, thanks, Bala. That's very beautiful and crisp introduction. I like that. So are we good to start?
Yes, the floor is yours.
Okay, thank you. Today, as Bala said, right? So there is a lot of content on RAG, and we know like we are grounding on RAG today. So how the journey would be, we would be taking is basically we see about what exactly is the basic RAG and what are the important components in that RAG, and then I'll start discussing about the problems that everyone would face while constructing this particular RAG pipeline from starting stage till the generation part of it, which is one of the component which I will discuss in few seconds from now. So our focus would be on learning what can be the potential issue and how do you mitigate that particular issue, but not compromising the accuracy or the relevance of the answers that you would get from a RAG perspective or a RAG pipeline. So this is the primary focus, and in this journey we would be seeing what is the naive RAG implementation would look like. We will also see the different experimentation that I myself have constructed as part of my PhD progress and all, and I have done a couple of experiments. I'll be sharing all those experiences with you. I've constructed a lot of architecture, so we'll be discussing we'll spend good amount of time on understanding the architectures, and then slowly we'll take on to the journey of from the just a second. Sorry, that's my kid. Okay, so we'll take it from the architectural discussions to the implementation parts of it, and then we will be seeing one of the problems that we discussed and how do we ground that particular problem with the different strategies that we apply, and we'll see some results on top of that. So this could be the entire journey, and finally we will be opening it up for questions, and then we will take it in the bi-directional way. I think like till that time, you have to bear with me. I think it will be a broadcast. Okay, so with that, let me share my screen now. Just let me know once you're seeing it.
Yeah, we can see it now.
Perfect. So so I don't believe in PPTs and all those things. So most of the time I put everything on my whiteboards. I share whiteboards. So and then I keep discussing them. So I don't have a formal PPT kind of things, but you will get a lot of knowledge from out of here. Okay, so let's start with the basic RAG. This is how the basic RAG would look like. So I'll give you the definition of a RAG at the end of this architectural explanation. Okay, so first of all,
can you zoom in a little bit?
Yeah, sure, why not? Just a second.
There's a zoom button on the video itself. Bottom right.
Also, could you set some context on like when do we think about using RAG? Like what is the right?
Yeah, sure. Yeah, I'm actually going to start on that. Yes. Okay. So here is what. Let's say you have you are assume that you are working on a specific domain. Example, I'm working on maritime. These days I'm into marine, too much of marine things and all. Like I deal with vessels, large cargo vessels and all. Previously I used to deal with aerospace. Now previously I'm in air, now I am on water. So so that time when someone comes and tell you that we have to implement an AI because GenAI has taken up a large leap in industry. So if someone suddenly comes and asks you, can we solve this particular problem over the GenAI technology or GenAI space? Okay, that's what is the biggest problem comes into picture, because we all know that LLMs, when they start training and then produce the commodity output like the general available LLMs, language models, they have something called a restriction, which is called cutoff date of knowledge, right? So suddenly you cut the knowledge, it's very difficult for an LLM to answer a domain specific question. And even if the knowledge is not cut off, there is some domain information which is private in space, okay, which is not even trained for an LLM. And those are the niche areas where this RAG would actually come as a weapon or a tool to solve those particular problems. Example, let's say if I ask what could be the technical specification of a primary display inside Boeing 737. Okay, so that's like very very confidential information, because those are like engineering architectures and low level specifications which no one will disclose outside of the world. Those will be inside Boeing or someone who is actually manufacturing it. Example, I used to deal with Honeywell, so I know that there are some specifications for that example. And at the same time, if you have a huge vessel, maybe I know Hyundai manufactures vessels. I don't know how many of you know. Recently, I came to know Hyundai. When it comes like you get cars, right? But these days, suddenly, I'm getting even the pictures of vessels in my mind. So, I have the proprietary architectures of the huge vessels. Just imagine vessel sizes of almost 427 meters, half a kilometer ship. So those vessels are manufactured by Hyundai. Okay, so now someone asked me a specific question on architecture. LLM cannot answer that because it's very much grounded to that particular architecture, which is not exposed outside. It's like IP, right? So these are the areas. These are the exact areas where you can actually implement RAG such that your architecture or your LLM will start knowing what is the context of your question, and then it will be able to search for that particular knowledge and finally able to answer or deliver or retrieve some kind of information and then present it to you guys. Okay, so this is the exact focus point where the RAG pitches in the NAA space. Okay, now with that particular base understanding of how we can bring in the RAG, now we know that it is all about the domain specific knowledge that's revolving around an LLM. Then how do you fit that particular knowledge on top of the LLM? Because LLMs are already having a huge amount of knowledge in them, right? So how do you superimpose this particular knowledge and then make an LLM to understand that it has to answer only from the knowledge, not from its prior knowledge, right? That's very, very important, right? So that is all about this basic RAG. Still, I didn't touch what is RAG definition, okay, or RAG expansion. But let me explain, and then I'll connect that with the RAG expansion. Okay. So now we know that, let's say, as a user, you're asking some query, okay, and you have a too much of knowledge, domain specific knowledge at your desk, right? So now that particular knowledge is what I'm representing as maybe a document here. Okay. Okay, I just wrote it. Okay. So this is the knowledge. And now what we do is basically we make the knowledge. We will not transfer the whole knowledge as once, because at any point in time for a given query, not the whole knowledge is responsible, but there are only few parts where you have to look into and then connect those dots to get the relevant answer. Okay, so that is where we call that as chunking strategy. Okay, so you chunk the whole knowledge into some parts and then push this knowledge into some kind of a storage mechanisms, which we call, you can, for now you can think these as databases, but these are special kind of databases which are called vector databases. So all these knowledge is being present in the vector databases in the form of vectors. Okay, just for now, just keep these terms in mind. I'll explain what these vectors are about. Okay, and now what happens is when a user asks the query, this query is also converted into a vector, and then we compare these vectors against the knowledge that we have ingested into. Then we get some relevancy chunks retrieved out of the knowledge that we will be passing into a kind of a template where you embed your user query, the retrieved knowledge along with some instructions, and the whole package of template we will pass it to an LLM, and the LLM will give you the final answer. So you're seeing the whole process here, right? So your knowledge first goes into some kind of a deep learning model, which is called embedding models. And I put a star there because that's the heart of the RAG. Okay, so that plays a majority of the role inside the RAG process. And finally, we send those embeddings into the vec stores. And then when the user asks, we'll use the same embedding model, get the embedding created, search that into a knowledge base, retrieve the knowledge, and this is the template that I was talking about, and finally give this template to an LLM, and then finally we get the response back, right? So this is the actual process that kicks in when you start implementing a RAG. Okay, now the expansion of the RAG is basically retrieval, augmentation, generation. Okay, retrieval, augmented, generation. Okay, that's the actual definition of RAG is. Now, why is it retrieval, augmented, generation? Retrieval is basically whatever you are searching in the knowledge base, we are retrieving it, right? So that's called the retrieval step. Okay, and then augmentation or augmented. Augmented is basically you are constructing this template with respect to the knowledge that's been retrieved along with your user query and few more instructions on top of it, and finally telling an LLM saying that please refer to the context for answering this particular question. That would be one of the instruction here. Okay, and never ever look at your prior knowledge. In case you are not finding the answers from the context given, just don't hallucinate, say you didn't find the answer, that's it. So those are the kind of instructions that we would write along with the context and the user query, and finally a LLM would wear the shoes that it will search for this relevancy inside the context that has been provided, and finally it would be able to answer. That is where the generation phase would come in. So that's called retrieval, augmented, generation. RAG is all about. So this is the basic RAG. And now let's touch a small basics on embeddings, what embeddings all about and what is these databases would favor us. Okay. Embeddings are like the heart, as I said, right? So what happens here is when you make these chunks or a kind of splits inside your knowledge, so these splits or the chunks, they go into the embedding model. This is just like any other neural network, the deep neural networks that we play with, right? So very similar to that, we have a deep neural network, and then you pass in. I'm not going to the depths of how that deep neural networks are constructed about. Maybe we can see it if time permits in some other sessions. But just now, you just think of it's like a black box of neural net, and then you pass in the chunks into that network, and you would get a matrix of one dimension. Okay, so I can say okay, if I say 1, 1, okay, it's like a row with 2 columns. It's 1 cross 2 matrix, right? So very similar to that, you have 1, 2, 3. Okay, so it will be like 1 by 3 matrix, 1 cross 3 matrix, right? So very similar to that, we deal with a higher dimensional matrix, which is like 1024, 1536 or 1538, which is like OpenAI's dimension, OpenAI's embedding dimension, which is 1536 if I'm not wrong. So those are the kind of a matrices that we, and even I saw some dimensions which go around 2048 or 2046. Okay, so those are the number of dimensions we get it. And here are 2 different embedding models that we may deal with, and we are going to deal with. Okay, so one is called dense vectors, the other one is called the sparse vectors. Okay, sparse vectors, of course, these are like, I mean, like by name itself, like they are clearly evident. Sparse is like there are very few numbers inside a matrix, but not everything. So if you have too many numbers, like every position inside the matrix is filled, it's like a dense matrix. So the sparse matrix, the example is, we call that as a best match BM24. Okay, so which is like a keyword search, and that is also represented as a one-dimensional representation of a matrix, right? So we deal with both of this, and we can combine these also, which will become a the next advanced architectures. Okay, so this is how the embedding model would work. So you just think you have a deep neural net, and then you passed in some information. Maybe you can pass a single string. Today I'm going to deliver a lecture on RAG. That's my single sentence, and then you passed it, and ultimately at the end of the other side, I'm getting a one single vector representing that today I'm going to deal with RAG. Okay, how this has been happening, because these embedding models are it's like a repository of the entire dictionary and then different data from the web. Okay, so just a sec. Okay, so we have a lot of data inside these embedding models, and then they start deriving the similarities from everything, and then finally you would get a single one-dimensional vector. That's all about how the embedding models would work, and finally you will get an embedding vector. Okay, and now comes with the vector databases. There are a lot of vector databases available, starting from Quadrant, Milvus, VV8, PineCone, Chroma, Fires, etc. Okay, and many more. I don't know if I forgot something, but there are good number of things. Okay, out of which Fires is from Facebook. Okay, and that's not actually a database, but it's a kind of a library. Okay, if you want to do some kind of a POCs and all, and you want to play around these concepts, you can definitely use that. Okay, but predominantly for production grade, maybe you can think the first Quadrant, Milvus, and VV8. So for entire this session, maybe for upcoming sessions also, we would be using Quadrant as our major source of vector storages. And what these vector storages would do is basically from the previous step, what are we getting? So we are getting a huge one-dimensional vector representation of the information that we have chunked and passed into it, right? So that vector, along with some metadata, this will store inside their storage or vector database storage. Okay, and what is the advantage that we get it now? Just imagine you have too many vectors inside this space, three-dimensional. You can just imagine three-dimensional space. Okay, and we call that as a latent space. Okay, and you have just imagine random spots inside this three-dimensional space, and suddenly you put one dot here, and then you ask the system, can you get me the relevant top 5 similarities? Okay, what we would do, it's very simple mathematics, right? We draw the distance between the adjacent all points, and then we derive the distance. It could be any distance, Manhattan distance, Euclidean distance, any distance, cosine similarity as well, cosine distance. So all these distance factors you can measure, and then finally you can pick like which are more close to the dot that you have kept as a new anomaly dot, right? So I want to measure this, and then we would bring these top similar vectors. This dot represents in a space, maybe like as a vector, like 1 dot 1 2 3 4, some number of dimensions, and that represents this particular number, the one-dimensional array. And then we have taken all the distances and then drawn maybe like top 5, top 10, top 20, all those things, right? So and then we bought those knowledge. That is what is the algorithm or the kind of a mechanism implemented in these vector databases. So vector databases basically perform your semantic search. Okay, that's the best word that I can use. Semantic search engines. They act as a semantic search engines. And when you deal with vector databases, there are many things to consider, like optimization techniques, and then you have quantization techniques and all those things. Maybe we discuss in the next classes, but I don't want to go too deep here on the first slide. So now you might have got a basic understanding of what exactly the RAG is all about. Okay, from a starting of a knowledge till the retrieval and then to a generation part, what exactly is happening inside this process, we have discussed it now. Okay, now let me go to a little advanced explanation of what could happen. Okay, now as I said, right, every step of a RAG is having too many problems in it. Okay, so now let's start. Your document can deal with what? Structured data, unstructured data. Okay, so structured data is all fine, no issues at all. But when it comes to unstructured data, there can be images, there could be tables, or there could be some kind of what I can say, infographics and all those things, right? So these are like very tricky things while you do parsing, when you do chunking strategies. So if you do a chunk strategy, you may miss one particular image which is actually connected to the previous context, right? How do you deal with those problems? That is the biggest problem that there in the very initial steps of document parsing. Another important thing is, how do you check the chunk overlap, chunk and overlap numbers? Chunking is basically the number of characters or the numbers that you want to split into, the size of the node or the split that you want to make over the knowledge. How do you derive that particular number? And there is one other concept which is called an overlap. So as I said again, you have split knowledge into, let's say, 5 different splits, right? One particular document has went into 5 different. So you always, it is a good idea to maintain an overlap such that you don't miss the contextual information between one split to the other split. Okay. So how much of overlap you maintain? Okay, that is the biggest question again. Okay, that is another problem. So you have 2 problems to deal with in initial stages, like what is your chunking strategy, what is the overlap strategy, and how do you come to a grounding solution on dealing with unstructured data. Okay, these are the 3 very important things when you start designing a RAG pipeline. Then come to embedding model. Which model to choose with respect to the dimensions and multilingual. Example, let's say if you're dealing with localization concepts, right? You have a document and that document is present in 5 different technologies. Okay, since I'm dealing with marine technologies now these days, so every document can be published in Portuguese, German, Chinese, Indian, English, basically. So all these same document, operations document will be there in this, because you don't know what kind of a crew is there on the ship. Okay, now if you want to do this RAG on those particular documents, now just imagine, because Portuguese, they cannot talk English so fluently. So they are very comfortable in typing or asking the questions in their own language, right? So this is what another biggest problem. And then how do you choose the dimensionality? Okay, so should I choose a model with 384 vector dimensions, or should I choose a model with 768 dimensions, or 1024 or 1536 or 2048? What? How? So this is another question. Okay, and now comes vector database. Now the data has moved on to the west. Imagine that you have grounded and then solved these 2 problems. Now it comes to vector databases. The problem here is, how do you properly index the vector database, and how do you tune these parameters of vector database such that your retrieval performance is at a top notch? Because 2 things. Your retrieval speeds should be not compromised, because no one has got the patience to wait until the bot responds. First one. Second thing, you cannot compromise on the top K, we call it as top K similarities that you are getting out of your search process. Okay, you cannot compromise on both of these things. Okay, this is the next problem. And then comes query ambiguity, right? So you're not writing a clear question, okay, for what you are trying to search it, or what you are trying to intended to ask. That's again a problem. Okay, and use of wrong or simple search methodologies. Okay, let's say you have used very simple search methodology. There are many things, as I said, right? Like I can combine a BM25 with a dense vectors. I told this statement, and I told, like, we will be discussing in later point in time, right? So this is called a hybrid searching. Okay, so if you are using a very simple search instead of any other methodologies, and you just imagine that it would work fine, that's a bigger mistake. Okay, and that's from a searching phase. Like searching phase also has got some problem. And then from ambiguity, so you have created instructions, but your augmentation phase is not so clear. Okay, then what happens is it has got a ripple effect on your generation. So faulty response by the LLM, as the augmentation and the retrieval gave a wrong context to feed into the LLM. Okay, so LLM will start inferring something else, and then it will finally give you a final answer which is of no use, and finally says that answer even is not up to the mark. That's what is most of the time users would actually tend to tell, or when you did some kind of experiment, you also might feel that, okay, the answers that are being given by an LLM are not up to the mark what I'm seeing, despite I've constructed 2 too robust pipeline of a RAG. The reason being is all these problems coming into picture. Okay, so it's our duty to focus on the problems and ground them at every phase, such that your pipeline would be on two things: one, robust, and then scalable. So these two things when you do, right, finally your answers that you get out of your LLM would be, at least I can say 90 to 95% accurate to the context that you are thinking. Okay, so I think like this is too much, right? So too many things that you have to address. It's not simple that you have a document, ingest it, ask a question, you get an answer. No. Okay, so now how do you start mitigating these problems? Okay. Okay. Okay, so now, as I said, mitigating the problems with hybrid methods. Okay, so what happens is basically, as I said, you have a document, and now I take two different embedding models, not single embedding model. Okay, these are different experimentations that I've done, and there are too many research papers published on RAG methodologies, and we have a lot of RAGs, in fact. Okay, maybe at the end of the session, I'll put that note, and maybe as a closing note, I'll quote them, and then we'll see it in subsequent sessions as time permits us. Okay, so now we have taken two different models, which is called dense embedding model and a sparse embedding model. Both will give you the respective dimensional vectors according to the model that you have selected. As I said, again, dense is like you have too many numbers in it, like it's a very dense packed vector of one dimension, not one dimension, maybe like 1536 dimensions and all. And sparse embedding models, yeah, you have very few things on the keyword matching, right? So keyword matching vectors, and both these vectors are stored inside the vector databases. Example, from now onwards, I will choose quadrant. When I refer quadrant, you just take it for granted it's a vector database. Okay, so in quadrant, I will be embedding these two vectors into the database, okay, or this engine. And when user asks, that also will get split into two, because the input is fed into the two models, and we would get two vectors. And now using these two, we would search our quadrant, okay, using the sparse vector, using the dense vector, okay, and then you would get the retrieval knowledge, and then finally you augment it and then send it to an LLM, and you do it. What is happening here is there are two things. One, with the dense vector, you are doing the similarity search, and with the sparse vector, you are actually doing the you are doing the keyword match kind of thing. So both the things are getting done at the same time. So the relevancy or the accuracy of getting the top K documents, which are aligned very close to the context of the question, increases drastically. Okay, so this is one of the method that you can deal it or experiment to increase the answer relevance at the end stage or the final stage. So final stage, we only deal with answer relevance. So what I should say, okay, in RAG, retrieval plays a very crucial role. So if your retrieval screws up, the entire process screws up. The reason being is if your retrieved documents are not of too much of relevance, then obviously your augmentation phase will ingest that context, and as an effect, the LLM will start answering on top of that particular context. So in RAG, we should be very careful in designing the retrieval aspect very strong. And of course, when the retrieval aspect is very strong, then your generation phase obviously will be very strong. That's a general perception. Okay, so this is one of the steps that we can deal with in order to mitigate the problems that we have discussed previously. Second one, most of the times when people talk about RAGs, they told, I mean, like, to keep on hearing, okay, you can fine tune an LLM for a domain specific knowledge. Okay, it's not joke. Okay, training an LLM is enormous, tedious thing that a developer has to go through, because he has to construct the data set that is understood by the LLM that he has chosen. And the chat template, maybe I don't know if you are aware of, there are maybe I'll make it more generic. Okay, any LLM, to understand the knowledge, you have to keep it in certain templates. Okay, these templates for an instruction tuned LLM, that's called a chat template. Okay, and these chat templates are different for different LLMs. When Llama from Meta, they provide instructions, they give you, this is the kind of a template you have to provide such that LLM can train on top of it. Very similar to that when you go to IBM Granite series or Microsoft Phi series or Mistral series. So everyone has got their own templates. So you have to create your data according to those templates, feed it to an LLM, go through some epochs, and finally your LLM would be ready. And that's not so easy. It takes months to get at least like say 90% of accuracy or 95% of accuracy. It takes time, and it takes even resources as well. It's not so easy. So you have to take GPUs, you have to run it. So yeah, if your data is too huge, maybe single node GPUs are not enough. You might have a cluster of GPUs, maybe 2, 3, something like that. So it's little tricky to train an LLM. I don't say it's tough, it's tricky to handle that. But instead of that, what you can do, because you're dealing not with LLM, but you are actually dealing with RAG. So what is important in RAG? RAG's important phase is retrieval. So why can't you tune an embedding model instead of an LLM, right? So if you tune an embedding model, now embedding model comes very close to your domain. So it can produce the vectors in accordance to the domain knowledge that it's been trained with. So which is very, very, very important in retrieval phase. And at the same time, it is very cost effective and time effective. Okay, because you don't need GPUs, it can run on CPU. You don't need months and months of time of training. It can be done in hours. And finally, your vectors are so closely aligned to the domain that your retrieval can happen maybe at 95% of relevance. We call that as relevance similarity or relevance accuracies. Okay, so that you can get it to a larger extent, right? So this is another step. So you can always look at training fine-tune embedding model instead of a language model, and you can actually check your what I can say, check your answer relevancy at the end, like how they are varying from a Navy RAG to a fine-tuned embedding model RAG. So this is how you can do a cross comparison. And for fine-tuning embeddings, maybe there could be a question from the audience. So you can go into sentence transformers, and sentence transformers officially these days announced the fine tuning of embedding models as one of the libraries into their documentation. So you can just go there, check it, and then you would get it. And then comes another way of doing it. So how do you chunk it basically? Okay, so since we talked about like chunking and overlapping, since we didn't talk about, we were talking on embedding models first, and then hybrid methodology of embedding models, fine tuning of the embedding models. But what about chunking? Chunking can be done in different ways. Like you can do it in sentence chunking, token chunking, recursive chunking, semantic chunking, late chunking, and slumber chunking. Okay, all these are different chunking patterns. Don't worry, you will see it in next slide. Okay, so and when you do about this chunking, again the same process follows, and you have to do a lot of repetitive experiments. One time you do with chunking, sentence chunking, the other time you do with recursive chunking, compare the results. That's how you draw comparative results of your knowledge against some kind of a data set, saying that okay, this particular chunking strategy gave me this kind of RAG metrics. There are few RAG metrics available from different RAG evaluation frameworks. Example like deep evals, ragas. So all these are RAG evaluation frameworks, like where they do something called answer relevancy, context relevancy, answer precision, context entity recall. So all these are different metrics that we measure on top of this pipeline by doing all these experiments. Okay, and come to the last architecture. This is a little tricky. The architecture 2 and architecture 3 are actually my research areas. I published some things, and then they are under review, and I've seen a significant improvement in the answers when it's been generating actually. So fine-tuned embedding model, even before sentence transformer produced its library, I've actually quoted this. And then additional sorry so now the entire process till augmentation is same, but what happened here is we call it as LLM ensembling. Okay, so we have 3 different LLMs from 3 different OEMs or the original providers. Like one LLM could be from 5 series, I say PHI 5 series from Microsoft. The other LLM could be Llama, and the third LLM could be from Mistral series. Okay, so these are 3 different LLMs, and what happens is this augmentation flows to these 3 different LLMs. Okay, and all the 3 LLMs, they think in different way, and then they intercept the context in 3 different ways, and you get 3 different answers. And now what we do is we even pass this context to a large LLM, could be your OpenAI's or Anthropic's. Okay, and now this has got the answer from all the 3 LLMs, at the same time the original context also, both. And now this larger LLM will have a capability, and we have an additional prompt attention also here, saying that okay, being as an observer or a judge, your role is to take maximum voting or maximum relevancy answer as top priority, something like that. So what it does is it will wear the hat of judgment, and it will clearly see, like, for this particular context, what is the answer that is being actually correct, and it will formulate its own answer based on that, and finally it will give you the final answer. So this would be the another way of tackling the RAG, where you improve what is being coming in and what is being produced out. So these are 4 different architectures which can actually solve majority of the problems inside the RAG pipeline that we have discussed, like many problems at the stages, right? So these are the different things that you can start implementing and ground those problems such that your efficiency of the pipeline goes to a next level. And comes now chunking strategies. Okay, so these are the names that you have seen. Okay, but before that, you have full source document, and then you have chunks extracted, because that's what we've been kept talking from last half an hour, like chunking. Okay, so how can you do chunking? There are a number of libraries available, or frameworks in fact. So couple of them, I love it. Okay, Llama Index. I'm a predominant fan of Llama Index. So Llama Index have got chunking strategies inbuilt, and then you have a LangChain. Of course, I'm the early adapter to write something called LangChain cookbook in my Medium articles. It's very early stage, Llama 1, LangChain 1. So, and lot many things have changed from then. So LangChain has got a lot of chunking strategies incorporated into them. And then you have a Haystack. Of course, I read Haystack, but I never attempted to write anything on Haystack. So Haystack is another one where you have chunking strategies, and then you can construct all these frameworks. Top 3: Llama Index, LangChain, and Haystack. These are the 3 frameworks view which, like, you can construct the entire RAG pipeline. Okay, but the bottom one, chunky, right? It is predominantly the chunking library. So you can do different chunking patterns, and then finally you can hook those chunks into one of the frameworks to ingest, and then maybe you can construct the RAG pipeline. So when you are combining chunky with these frameworks, then you don't need to take the advantage of inbuilt chunking and ingestion phase of those frameworks. In fact, it is delegated to the chunky library. Okay, so chunky gives you these specific set of different chunking strategies. Okay, and why we have chosen chunky? Because their benchmarkings are too good. Okay, so when compared to the standard libraries like your LangChain, Llama Index, Haystack, and all these things, right? So they are like 100x, 60x, 45x better than all these things. That's what is their benchmark. Maybe I'll provide you the GitHub repositories of all these things. Maybe you can see it on your own. Okay, now coming to the token chunking. Token chunking is basically just to chunk it based on the tokens, and then giving you that split, okay, of one particular chunk out of it. And if you have a whole document, then we will say these many chunks I need it, and then you get those many chunks. Okay, it's very simple. That's basic chunking strategy available in chunky. Then comes the sentence chunker. Sentence chunker is basically you can induce the rules, like where the sentence ends based on the punctuations that you have in English, right? So it splits the chunks as sentences by by grounding the sentence boundaries as well as semantics both. Okay, and recursive chunking. Recursive chunking is basically it has a recursive loop to chunk on the chunk boundary. Okay, so it goes into a recursive loops to check like how much of chunk I have to produce based on some of the parameters that you pass, like the chunking rules. It could be chunking rules, or it could be document sizes, the number of characters. So there are couple of things where you pass in, and based on that it will take a decision where to chunk it and how best I can do it. Okay, then comes the semantic chunker. Like these three, token chunker, sentence chunker, and recursive chunker are there from the initial versions of RAG or the initial versions of the libraries like Llama Index, LangChain, everything. When they started their journey as an inception, these are there. But the later three, which I'm going to discuss, or we are going to discuss now, are the newest inventions or the new papers that came into picture, and then all these frameworks got accustomed or inculcated these methodologies also. First thing is semantic chunking. Semantic chunking is basically, say, example, you take best examples are medical documents or legal documents. Okay, so you have 30-40 pages of document or even more sometime, and you have some context on page 5 which is actually relating to page 28. Okay, so if you do on standard chunkings as top, like sentence chunking, recursive chunking, or a token chunking, these context of page 5 to page 28 will never be fulfilled, and it is always a huge gap. Okay, and at the time of asking a question, doesn't matter how many different architectures you implement, it will never be retrieved. Okay, so this is one of the best strategy that came into picture. Okay, as a semantic chunker, what happens is basically we take a models and then do a semantic similarity of the sentences and club those same meanings as one and create a chunk out of it, which is very, very, very great thing that happens in semantic chunking. And then comes the late chunking. Late chunking is an architectural style actually published in a recent papers.
Quick time check, 10 minutes.
Yeah, sure. I'm sorry, I think like we couldn't get even a time to show you the code actually. So I even prepared a lot of code for you guys, but yeah, too much concept actually. Okay, fine. So late chunking, maybe I'll be quick here. So late chunking is something, whatever you have seen in the previous architectures, right? You are passing in the doc and finally you are getting a chunk, but it is in a different, I'm sorry, you are passing in a doc and you are getting the embeddings, right? Or chunks. But what happens here is, you actually get the whole embedding or a chunk for one particular document, and on top of that you have n number of chunks split on top of it. So it is like one big chunk or a embedding. On top of that you will get n number of embeddings, which is called late chunking, because chunking is happening after you did the entire document processing. Okay, so that is called the late chunking. Maybe we'll see it in practice. And then neural chunking, again we fine tune some BERTs, okay, and then pass your document in those fine tuned BERTs and finally give the chunking strategy using some neural network models. And then slumber chunking is basically from the agentic perspective. So you have an agent, it looks at your document and takes a decision like where to chunk, where not to chunk. So it's like more advanced than every other chunking. Okay, these are all about like the RAG patterns, starting from your Navy RAG, how we started on the domain knowledge and grounding your LLM only to that particular knowledge, till the strategies of how you can actually choose some patterns to make your RAG pipeline more robust and accurate. Okay, so with this, maybe we can open up the questions. Meanwhile, I'll also bring up my IDE and then show some kind of code base for you. But let's open up for the questions now.
Super. Folks, I saw that some of you wanted to extend, so we'll leave it to Pawan after addressing some of these questions. If Pawan has time.
Yeah, I have got time till 11:15.
Sure, sounds good. So let's quickly go over some of these interesting questions. First of all, there was a very, very loaded session. I had to pay very close attention. Thank you for that, and it shows the preparation also. Yeah, we'll start with the first thing. So Gautam asks, with the context windows increasing from 128K to 2 million and beyond, does that impact RAG in any way?
Yeah, so good question. Actually, there's a lot of noise around that actually. Impacting RAG, yes, it would impact RAG. So see, if your LLM's context window is very low, I think like previously it used to be 64K and now it has went to 1 million also. Okay, so just see the shift, 64K to 1 million. It's like huge shift. So in that 64K itself, like if you can fit the right context into it, it would be good. Like the LLMs answer in very much relevant to your questions and all. But now since it has went to 1 million, there is a debate and saying that, okay, RAG is dead, and then you can pass the entire document into it, into the LLM, and then you can do it. Like this chunking and all is not necessary. But when you do that, there is always a possibility of hallucination coming into picture, because it's seeing huge document at once. Example, let's say, as I say, right, contractual agreements like your NDAs, non-disclosure agreements. I saw yesterday there is one NDA which is like 74 pages in size. Okay, so if you just pump that particular document and ask some question, no, so if your top-notch models can actually ground your answer, saying that Gemini Flash 2.0 and then maybe your OpenAI 4.1 or O3 mini or O3 high as well. So if these kind of models can ground it, but what if suppose sometimes you don't want to share this and then keep the infrastructure at your local machine? Not when I say local, it's about corporate. So you're self-hosting. That's what I meant. So you cannot bring that huge models, right? So you will reduce your model sizes. That is where the trick comes in. So it may not answer rightly, because I was dealing with one of the problem statement in medical domain where we are passing the pre-authorization form and then insurance claims. We want to match both of this, and then we were not getting good results. But as I said, like when we are giving it to Google Flash and then OpenAI, we are getting excellent results. So this is the another thing. So how best you can implement the RAG now? Since even though we have 1 million context window, it's not actually helping us, right? So of course, yes, you can pass your request response sizes can increase now. So you can have a conversation where you can have a elongated conversation because your context windows are high, but context window increasing may not help you get the exact answers. But even though you have a long context window, you should also implement a RAG such that your questions get answered in a very accurate manner.
Perfect. Cool. Just moving on to, I'm going in different order, guys. Questions. So one other interesting one I see, when do you go for RAG versus fine-tuned LLM model?
Awesome.
What is the cost and other aspects? But there are also some performance aspects, if I understand. Yeah, please go ahead.
Perfect. This is excellent question. So when we want to go for a fine-tuned and this one, right? So it's something like this, right? So if you want the base model itself to be more aligned to the domain, and on top of it you can start superimposing your live data. Okay, so that is the scenario where I find the LLM fine tuning is more needed. Example, I was dealing with one of the problem statement on localization. Okay, so we have an LLM and we want to fine tune it with the because we are not going to change some of the grounding concepts. Okay, and there is no meaning that we start implementing a RAG, because our information is not changing as such in a too drastic way. So example what that is our product user guides. Okay, so that will not change too often. Okay, so what we did is basically for these scenarios where you see the information may not change too often, I think you can take these data, as I said, the process of fine tuning, right? Convert that onto a template and then put it onto an LLM and then fine tune it. This is one scenario. But whereas you see a scenario where there is a streaming of data, too much of data comes in, and then your model can drift the accuracies late recently. So that is the scenario where you can see the advantages of RAG over the fine tuning. So these are the two different scenarios, at least like what I have encountered. maybe this is just like a suggestion. I'm not answering it. So maybe you can also think of it. But these are the exact scenarios I faced and I felt it.
Perfect. Thanks. One other interesting question is, how do you deal with structured data? RAG.
Structured data. This is awesome. All the three are top-notch questions. So structured data, when we call it right till date, all the data is in sequels. Okay, so because over the 2 decades of software engineering, what we have done is pure CRUD, right? So most of the data is in sequels, and that is where like dealing with structured data is more important, because too much of domain-centric data, customer data, or maybe if you are dealing with e-com, so everything is residing in our SQL databases like your Postgres, Oracle, MySQL, blah blah blah. So now, how do you deal with that? Is basically there are n number of methodologies, and these days agents being more focused. I think frameworks like Agno or frameworks like Crew AI, they have given a good methodologies how to solve the structural data problem. So I'll tell you in a very high standard or a high level, maybe from a 40,000 feet high, I'll tell you like how you can do it. First of all, what you have to do is we have to give a something called a knowledge base as one of the file, saying that, okay, these are some queries. Okay, this is like a knowledge, and then this kind of an answer can be bought by this particular query. Okay, a set of bunch of queries. Okay, and then we will expose the schema structure of the LLM, maybe your ER diagram kind of thing. Okay, fuse these two things together, put it to an LLM and start asking the question. And now what it does, it will try to retrieve the semantics from the knowledge that you have given, and it will try to correlate with the schema structure, and then start inferring the real tables and relations from the actual database and the semantics from the knowledge that you have provided, and it will try to start creating the sequels for you, and then finally review. And at the same time, if you can start infusing Ripple kind of a tools to it for an agentic behavior, what it does is even before it prompts the answer to the user, it will start executing the SQL queries in Ripple, and then if there is no syntax error, then only it will start confirming, okay, this is the exact query that you can try it with, and this is the answer that you could get in. So this is the, and when I say schema structure, it is not about the tables and the relations, but you can also expose it the columns also, columns and data types. So now what happens is everything about the database is known by the LLM or an agent, and finally it can ground exactly to the questions that we are asking. Okay, so this is one way that agents would solve it. Of course, LLM can also solve in the same way. We have something called SQL Alchemy, right? So if you can start SQL Alchemy libraries into this RAG pipeline, they can also give you, but not too ground. I think there is something called Versal AI or something. I just forgot the library. They have actually claimed, right? So for the SQL, NL to SQL, natural language to SQL, I think they have claimed a very good accuracies and all. Maybe I'll post that in WhatsApp group to Praveen and Bala after that, and then they can circulate in the group.
Yeah, for sure. So before we get into other questions, right? So a lot of folks have asked for some of these material, especially your Medium link and the reference to some of these packages that you actually spoke about. So if you have any content, do share it with us.
Definitely. I'll do that all this. Maybe I produce this my drawings as well.
Yeah. So that'll be very helpful. We'll send it across, put it up on the website.
Yeah, research papers as well. I saw that.
Yeah. So we'll definitely do that, folks. One other interesting question I see is what kind of observability or evals will you build for the RAG systems?
Perfect. I think I thought of covering in the next session. So this is one part of the ball game, but the other part of the ball game is how do you deploy this, and how do you start observing this, and then what kind of metrics that you evaluate on this. So these are the three major things when you take this RAG pipelines onto the production environments, right? So creating an experiment, doing a POC is one part of the section, but taking that when you feel that confidence that it is giving you a good amount of accurate results, so it is lifting this and putting it into production is a different part of the section. So for observability, I have actually experimented on 4 different tools. starting from your ML flow, LangFuse, Aris Phoenix, OpenLit. So all the different tools we have experimented, and then I've got good hands-on on top of all these things. So we can see a lot of different aspects in different tools. Those are tool-specific things. But out of all these things, LangFuse is very robust. Aris Phoenix is very strong, and ML Flow is also very strong. OpenLit just started its career; it's like new in the market, and then they are also doing good. And this is from the observability perspective. Coming to the evals, as I said, right, two libraries you can trust on them. One is Ragas and the other one is deep evals. Okay, so and each one of them have almost 15 to 20 different metrics, and you have to carefully choose what metrics are relevant to you. Not everything is relevant for every use case, right? As I said, there are metrics for retrieval, there are metrics for generation. Okay, these are two different phases. Okay, so you can choose 2 to 3 different metrics for both retrieval and generation, maybe a total of 6 metrics, and you should constantly measure on your RAG pipeline. Couple of them, your contextual relevance, context entity recall, these are retrieval metrics because context comes only at retriever phase, right? Answer relevancy, and then faithfulness. These are like generation part of generation metrics, right? So these are 4 metrics, and there are other things which I forgot, but yes, we have metrics and we have libraries for doing that.
Got it. Perfect. Cool. So, about update. No, I mean, how do you do knowledge updates and probably feedback loops based on customer feedback when you use RAG? Like for example, so let's say I have exposed my application to the customer, and how do I update my how do you say workflow based on the customer feedback, whether it is relevant or not, especially when you're using RAG, or let's say the knowledge base update gets updated.
Okay, perfect. So what we do is basically, or what I did basically, that I'll tell you. One second. Okay, so example, you assume that one of the RAG pipelines is already in their production, and then people are starting using it using some kind of a bot interface, and we have something called a feedback mechanism. Okay, that's the most main thing that we do. So if at all like people say it is accurate on the time scale or a rate scale, or whether it is good versus bad or something, like it satisfied your query or it dissatisfied it. So these, it's like a binary 1 or 0, right? So these kind of feedbacks you have to collect, no other way. And once you collect them, what we have to do is every query in the background, as I said, like we have a eval pipeline. So when user says is dissatisfied, we have to cross check that with the eval query, and that is run by the tracing. So for every question there is a trace that happens, and for this trace, what is the retrieval that has happened, what is the context it has picked. All these things we will be doing as a background activity, and very similar to the normal software releases, we do have it as a specific releases. So once we evaluate and get some kind of conclusion, we tune the hyperparameters. Now comes the question actually. So right, so in RAG, what are hyperparameters? Because hyperparameters as such in neural networks or deep learning or machine learning, we know it. But what are hyperparameters in a RAG? RAG is a procedure or a process or a pipeline, right? So what are the hyperparameters here? That's the biggest question, right? So you have something called top K. We have repeated this word too many times in the retrieval. So that's a hyperparameter. How many top K I have to put such that your relevances are too accurate, right? And then you have embedding model. What kind of embedding model I have to select? What kind of a chunking strategy? What kind of a chunk overlap and chunk number itself, like how much of chunk length? And then what are the instruction set that I have to put in my augmentation phase? Okay, and what is my temperature LLM? What is my top P? Okay, and what is my penalty score? So all these from an LLM perspective. So if you take the entire process, there are hyperparameters at LLM, hyperparameters of chunking level, hyperparameters at the embedding model. So these are all the things that we actually tune as part of this debugging. Okay, so if something is not actually retrieved in a right fashion, something is not actually coming in a not satisfying manner, so we actually go to the observability platform, we trace it, what is being happening at that particular time, and then do some kind of a modifications and then see why exactly. Maybe your indexing is not happened in right way in vector databases, that could also give you a wrong results. So these all things that we see, and that's how we have to ground.
Perfect. Super. All right. Probably we'll wind it at this time. Folks, any other question before?
And I don't know, I should say sorry because I couldn't get much time. So you see just for now you see it, maybe in the next session I'll show you a lot of code. It would be of code intense session then. So you see it like we have chunking strategies. So you have a lot of chunking strategies, and then you have context enriched retrievals, and then you have something called a fusion RAG. You have a hide RAG and lot many RAGs. Maybe I'll tell you the mechanisms of RAG in the next session, maybe whenever Praveen
we can do a third session also, Pawan.
Yeah, sure.
GMK has a question. Sorry, GMK has
one last question. Sorry. So we were talking about getting this similarities as part of retrieval. Now let's say there are multiple chunks which has similarity above the threshold, and we are passing all these chunks as part of augmentation. Do we also pass the similarity score for the LLM to understand that, hey, some of these are more similar, some of these are less similar? Is that information passed to the LLMs in some way?
No, that information is not passed to the LLM. In fact, that would be done as one of the prior step, which we call it as a re-ranking. Okay, so I think like all the questions, these are like very good. Actually, I'm very happy to listen all these questions. So what happens is you say that there are like maybe 23. I'm very particular on the number, right? Okay, I don't want to put a round figure number. So you have 23 different documents retrieved as part of similarity. Not everything is highly similar. Not everything is 90% similar, right? So there could be a minute floating point decimal variation, saying that first one is at 82.12, and the second or third or fourth would come at around 76.82. Okay, maybe further down. Now what we do is, it doesn't mean on the first retrieval this relevancy score doesn't mean they are very much apt as a relevant document. What we do is we do a re-rank, we superimpose a re-ranking algorithm on top of it. What they do is they will re-rank this according to the question, how much similarity they are met. The context is how much similar to the question asked. Okay, and then they do the similarity among these contexts that have been retrieved among these interchangeably, and finally they will do a shuffling over this entire context array, saying that maybe the seventh one, which is at maybe 62% of accuracy, would suddenly become as a top accurate one. And that's how once the re-ranking chunk of arrays would arrive, on top of that maybe we can take top 10 and then produce it to LLM. Now LLM is not intended to know what is the accuracy. Maybe if you provide that, that will become a bias. Okay, so we don't want to do that, and we will chop the information there, and we'll just provide you, okay, this is your context, because we know that we have done a pre-processing, enough pre-processing, and we know that the documents which are there on the top are highly relevant now. That's it. And then LLM will give you the answer.
Got it. Thanks. That helps. Thank you.
Super. Pawan, thank you so much. This was an extremely high density session. Love it. I think at least I see myself going back and rewinding and like looking at a few parts. And thank you for taking the time and putting in the effort and coming and sharing this with us. Really appreciate it. We'll share it with the group. We'll also post the video so more people can benefit from this.
Always. Thanks, and nice meeting with you all, guys, and the questions are awesome. And let's meet on the next session on code intense session, not on theory intense session.
Done. Super. All right. Thank you.
Thank you all.
Thank you all. Bye.